Module 2, problem number 11. Suppose the lengths of the pregnancies of a certain animal are approximately normally distributed with a mean of 258 days and standard deviation sigma equal to 23 days. Complete parts A through F below. Part A, what is the probability that a randomly selected pregnancy lasts less than 251 days? Well, first, we're assuming it's normally distributed, but we don't have a standard normal distribution. That means we can't use the standard normal distribution table or that Z variable yet. But what we can do is use StatCrunch. So let's go ahead and go to question help in theory. There we go. StatCrunch. We're going to make this a little smaller. We're going to go to stat and calculators, and we're going to go down to normal. See our nice little normal distribution here. So it's saying we were given a mean and a standard deviation. So we are going to switch this from 0, since we don't have standard normal distribution. We just have normal, 258 to 23 days. 23. Let's make this a little smaller so we can see all this together. All right, so now we've got this set up. Now we want to know, what is the probability that randomly selected pregnancy lasts less than? When it says less than, we know that we are looking to the left of that X variable. So we're going to put 251 in here. Now, just looking at this, we know that it should be less than 50% or less than 0.5 probability, because we know that this is to the left of the mean. If we want to know what the probability is of it being less than the mean, that 258, that would be 0.5. So we already expect this to be less than 0.5. So that's the first tip to kind of do a reality check on our answer. Let's click compute. It is less than 0.5, so it's kind of in the range we were expecting. So let's go ahead and round it to 4 places and check our answer. 0.3804. Check answer. Good job. All right, interpret this probability. Select the correct choice below and fill in the answer box with your choice. This is saying if 100 pregnant individuals were selected independently from this population, we would expect blank pregnancies to last more than 250 days, to last exactly 250 days, or to last less than. Well, we already know that we found the probability of it being less than 251 days. So we know right now that our correct option is C. Now, how do we put that in? Like, what number are we looking at? Well, this is our new N, right? We're saying if 100 of these pregnant individuals were selected, we would expect, that's our probability. So we need to multiply 100 by 0.3804. And does it say, it says round to the nearest integer. So if we round that, we get 38, because 0.38 times 100, or 0.3804 times 100 would be 38.04. But once we round it to the nearest integer, we get 38. Let's check our answer. Nice work. All right, part B. Suppose a random sample of 24 pregnancies is obtained. Describe the sampling distribution of the sample mean length of pregnancies. So the central limit theorem tells us that regardless of the underlying population, the sampling distribution of those sample means. So if we were to take now, well, let's not get into too much of this. We know that the sampling distribution of X bar is going to be approximately normal. That's what the central limit theorem tells us. Now, we also know from that, let me get here we go. So let's take a look at this. So we know that the mean of X bar is the same as the mean of the population. Now, we also know that sigma X bar is equal to sigma of the population divided by the square root of N. So in this case, we know that the mean is going to be the same, which was 258? All right, now we need to do the sigma. So we had our original standard deviation was 23, and now our N is 24, right? We're pulling a sample of 24. So we're going to say the square root of 24 on the bottom. Now I put that into my calculator, and let's see what we get. All right, we're going to get 4, and we need to round to 4 decimal places. So we're going to go to 5. So we have 4.69486. When we round that, we get 4.6949. So let's type in our answers and make sure we're correct. We have 258 for the mean of X bar, and we have 4.6949 for sigma X bar. Check our answer. Nice work. Wonderful. What is the probability that a random sample of 24 pregnancies has a mean gestation period of 25 days or less. 251 days or less. Now, I want to point out the difference. Up here, we were looking at a randomly selected one pregnancy. That means we could use this original population data. Here, we're now talking about a sample. So now we have to use these numbers we just found as our new mean and standard deviation when we calculate that probability. So here, that mean stays the same because remember, mu x bar equals the mean from the population. But our standard deviation is no longer 23. It's 4.6949. The idea is that now we're not saying what's the likelihood that a randomly selected pregnancy lasts less than 251 days. We're saying what's the likelihood that the mean pregnancy of these new 24 people is less than 251. All right, so we're going to click compute, and it's going to give us that 0.067, or here, let's type that in as I'm saying it, 0.0680, because we need to round up. So let's check our answer. Good job. All right, interpret this probability. Select the correct choice below and fill in the answer box with your choice. All right, if 100 independent random samples of size n equals 24 were obtained from this population, we would expect blank samples to have a sample mean of 251 days or less. Now, we already know that's our option because we found here that they were less than 251 days, so we know 251 or less. We know it's not exactly 251, and we know it's not 251 or more, so we know we're looking here. So now let's multiply our 100 by that. We're going to get 6.8, and it says round to the nearest integer. Once we round 6.8 up, we're going to get 7. Check our answer. Fantastic. It's very exciting to get immediate feedback. All right, part D. What is the probability that a random sample of 70 pregnancies has a mean gestation period of 251 days or less? Again, we are looking at something very similar as we just did, but now what changed in this? Our sample size. So since our sample size changed, that means our new sigma x bar will also change. So here we have 70 square root on the bottom. And one thing I want you to notice is our standard deviation is going down as we increase our sample size. That means as you increase your sample size, you expect there's going to be less spread in your data. That's an important observation. Sample size is very important. All right, when I put this into the calculator, I get 2.74903, and we are rounding to 4 decimal places. So since that's less than 5, we just need to put that number in. So let's see. Now it says so that's what we know is going to be our new sigma, and we have our mean for when we want to compute this probability. So we now need to put this back over here. Again, our mean stays the same because the sample mean, or the mu x bar, is the same as the mu of the population. So here we have we're going to put in our new 7490. You can put that other 3 in there. It doesn't worry about running because we're not inputting our answer into MyStatLab. We're going to click compute and see how that's very small. Again, much more of your data is going to be around the mean at this point because our standard deviation is so low. So we would expect those tails to be very small. We expect to have this probability go down and down and down and down. All right. So we're going to put in 0.0054. Check answer. Fantastic. All right. Interpret this probability. Select the correct choice below and fill in the answer box with your choice. Again, if 100 independent random samples of size n equals 70 pregnancies were obtained from this population, we would expect blank samples to have a sample mean of 251 days or less, exactly 251 or 251 or more. Again, we found it for less than or equal to 251 or less than 251, so we know this is what we're looking at. We need to multiply 100 by this number. When we multiply 100 by this, we get 0.54. When we round that to the nearest integer, we round up to 1. Check our answer. Nice work. Again, notice as our sample size is going up and up and up, we expect fewer and fewer sample means, not just pregnancies, but sample means to be at 251 or less or farther from that mean. What might you conclude if a random sample of 70 pregnancies resulted in a mean gestation period of 251 days or less? It says the results would be blank, either expected or unusual, so the sample likely came from a population whose mean gestation period is greater than, equal to, or less than. Now let's think about this. We're saying that the probability of this occurring, of that mean gestation being less than 251 for a sample of 70 is 0.0054. That means it's extremely unlikely. We do not expect that. That is unusual. That is not expected at all. So it's very likely that the population whose mean gestation period is actually less than 258. All right, let's check that answer. Well done. Holy moly, we still have one more part. What is the probability a random sample of size 19 will have a mean gestation period within 11 days of the mean? Ooh, this is kind of fun because now, instead of just looking at, let me show you. Don't judge my normal distribution drawing. It's usually horrific. So before we were looking at this period or that region. Now we're looking at this, where this is our mean, and we're looking at 11 days to either direction. Okay, so since our mean is 251, this is where we get to switch this to the between. So let's say now our mean is still 258, but we're looking for it to be, let's see, 258 minus 11 gives us 247, and then plus 11 gives us 269. But wait, does our standard deviation change? Did our sample size change? Oh, our random sample is size 19. So our mean doesn't change, but let's go back and make sure that we have the right standard deviation. All right, so our standard deviation, sigma x bar equals, again, sigma over the square root of n. What was our sigma again? That was 23 days over the square root of 19. All right, so let's put that into our calculator. And that, that is 5.27656. Now notice our sample size is smaller. It's only 19. Our standard deviation is much higher than it was with the sample size of 70. It's, again, you notice that stuff. That's important. 5.27656. All right. So now we have our mean, which is the same as the population mean, and our new standard deviation, and we have this is within 11 days. So let's go ahead and click compute. Nice, that look at that nice visual that tells us we really expect it to be within 11 days, right? The probability, round to 4 decimal places, is 0.9629. Check answer. Nice work. So that's something we would actually expect. We would definitely expect that random sample of 19 to have a mean gestation within 11 days of the population mean or sample mean. So if anybody has any questions, let me know. Again, that's module 2, problem number 11.